Math is a wonderful thing. Math is a really cool thing. So get off your ass and do some math, 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 math. Well, welcome to this crazy yet zany podcast, beginning with yours truly, Mr. Stewart. And math is a wonderful thing. I don't suspect that's going to hit the top of the charts anytime soon, but hopefully you enjoyed that little introduction. Today's podcast is concerned with a couple of things. One is to apply a formula for the dot product with regards to the concept of work and also in finding the angle between two vectors. We also need to develop a formula for what we call vector projections and then apply this formula. So um, I omitted or forgot to give you the handouts to these today, but they are posted online to the website. So if you have a chance to print them off, that would be great, and or wait until tomorrow. The only thing is that you'll have to take down whatever notes you can now and possibly add to the notes for tomorrow. So in the first example, which is entitled We Can Work It Out, of course that is the name of a Beatles song, we have an object that's being dragged 5 meters up a ramp. Okay, that's under a constant force of 30 newtons. The force is also being applied at an angle of 40 degrees to the ramp. We need to find the work that's been done. So you might recall from a previous lesson that work is the product of the force required to move an object, and we are moving the object in the direction of, well, whatever direction has been designated, and that's being multiplied by the displacement of the object. Okay, so with regards to our ramp that we have here below, we have a right angled triangle. Now, as far as the force is concerned, okay, we're going to have a vector. I'm going to draw its tail here at the base of the triangle. So we have this vector trailing off here at an angle of 40 degrees to the ramp. Okay, so let's indicate this as 40 degrees. Now we also have a displacement. So I'm going to indicate the displacement vector on here as well, but I'll use a different color to do so. Let's go with blue. Now the displacement is in the direction, and that vector doesn't look like it came off as being blue. So let me go back and change that a bit for us. There we go, much better. Now I've drawn the displacement vector to be longer than the force that's being applied. Now the length of that vector really doesn't matter, okay, in this particular case. And you're going to see why in the next example when we work with vector projections. But for the time being, what I'm going to say to everybody is the following. I'm going to take this same force vector, I'm just going to do an overlay here, and I'm going to change the color of that vector. Let's go with a nice bright red. So what we're going to do is we're going to have to find out the projection of that vector onto the displacement vector. So let's say that this is the displacement vector here. Okay, what we had originally in black, let's call uppercase F, which is the force, the resultant force, which is responsible for moving the object. But work is specifically the product of force applied in the direction of the object. Okay, so what that means is we need to, let me drop a perpendicular down here to this axis, and you'll see why in just a couple moments. What I'm going to do is take the head of this vector and I'm going to basically translate it down without trying to change its length. Let's try that again. There we go, that's what I need. Moving it down, okay. I haven't changed its length yet, okay. Now, consider where that vector is now, okay. I would like to call that vector the component of f, okay. I'd really like to be able to say that this is a horizontal component for the vector f, but I can't, okay. What you can notice here is that I have drawn in this vertical component here, and we know that the vertical along with the horizontal component produces the resultant force. So that means I need to scale this vector back until it meets up with the tail of the of the vertical component, which we have here. So with that being said, what we have now, we have displacement. Notice I'm color coding here. We do have the scaled back version of vector f, that is uppercase F. This would be the length of that horizontal component. So in a nutshell, we really already do have all of the material, the values, the process required to solve this problem. Okay, so what I'll do is I'm just going to fill in a few blanks and I'll have you go back and make the calculations on this. So the displacement is 5 meters. We can indicate the units now, or we can do so later. I'll put them in now. Typically I do not, I usually wait to the end. And then F cos theta, the magnitude of the force is given. It is 30 newtons. So we're going to have 30 cos theta is 40. Okay, and that would be in terms of newtons. So I'm going to put another set of brackets in here. And at the end of the day, what are you going to end up with? Well, I'll allow you to do the multiplication, but I know that 5/30s are 150. I'll let you assess cosine of 40, and that's in Newton meters, which is also a measurement of energy as well as work in joules. So I'll have you go back and you can complete the calculation. Okay, so I know we've already tackled the concept of work, but it is an application for the dot product. And remember that this here, this is the dot product. And moreover, it is an application of the dot product. Now, in moving to the next example, we can find magnitudes, scalar products like work, but the formula that we're given also is useful for finding angles. So here's what I have for us right now, is let's consider that you had a problem concerning work or some other physical quantity, and you had to find the angle. This example here would be the one to help. So consider these two vectors, A, 3, 5, and B, minus 7, 4. Our task is to find the angle between them. Well, we do know that the dot product geometrically is defined as the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between the vectors placed tail to tail. So if we want to solve for the angle, well, we could therefore divide both sides by those magnitudes. And following that, we could then take the inverse cosine of both sides of the equation, and then we would end up with an expression that would allow for us to solve for angle theta. Okay? Now, we could possibly go one step further, and that is to say, if I am given this expression here, I could also replace that with something else. Recall that based on the proof from, I think it was page 370, I want to say 74, I could be wrong, that when you find the dot product of two vectors, you can also add together the products of their x components along with their y's. So if you don't recall this one, look back in the text on this particular proof. It's in section 7.2, I believe, if not 7.3. So we could take that here. I'm going to color code those parts that are equivalent, and we could write ourselves a new formula. We could take the inverse cosine of these, and we would have ourselves an answer. So what I can do is we can set this up, but I would encourage you to go ahead without my tutoring per se with this example and see if you can come up with your own answer. Okay, let's have a go at starting this thing, and then I'll have you guys come back and finish things off. Okay, so let's work with angle theta. So we have the inverse cosine of, now up top, the A1, B1. So let's go with red on these. Here's the A1, here's the B1. So we're going to have 3 by minus 7. Okay, and to that we're going to add on A2, B2. So A2, B2, 5 fours, making 20. Okay. Now underneath, this is where you're going to have to do a little extra work. We need the magnitude of vectors A and B. So I'm just going to insert a slide here right now. And recall that the magnitude of A, so if vector A is given as A1, A2, okay, then the magnitude of A is simply the square of each component and then adding those together. Okay, so the same thing would go for B. So given B, B1, B2, we see that the magnitude of B is going to be B1 squared plus B2 squared. Okay, so I need you to go back and perform those calculations and then insert them accordingly, which of course is here and here. Follow through on the calculation and write your answer down to, say, the nearest degree. Now, prior to moving on, I am reminded here right now, that is reminding myself, I have forgotten one little thing, which will change a whole lot. Don't forget those radical signs. Okay, my apologies on that one. Okay, the expression that I gave you earlier on would have been the magnitude of a vector squared. These are the correct forms for the magnitude of a vector. So of course, again, make those calculations, go back, insert here and here, and solve for theta to the nearest degree. Now we're up to 14 minutes. I'd like to venture into the next segment. So I think we'll save this one as its own file, and then we'll start up another one.